Okay, YouTube, in this video we're going to introduce and use the properties of logarithms, or what we call the properties of logarithms, of which there are three primary ones: our product, quotient, and power properties. And so essentially, because we know that logarithmic functions with a base of b are inverse functions of exponential things that have the same base, that is to say that these things are inverses, then they're not going to have properties that are too far different from one another. So that is to say that at least with exponential things, let's go ahead and do this. Properties of exponents would be these properties here. We would have x to the a times x to the b if we multiplied two exponential things having the same basis. Recall that we add the exponents here, whereas if we were to divide two things that have the same basis, we would subtract their exponents. So a minus b power, where this would be a plus b power. And then our third property, this is our product or quotient, we also have a power property when it comes to exponents. X to the a to the b would be x to the a times b. So kind of reviewing these three properties of exponential things, or exponents, when we look at the properties of logarithms, we're going to see some similarities occur, because remember that a logarithm really is an exponent. So let's go ahead and take a look at these three properties here. And they say that letting b, m, and n be positive real numbers, and of course we never allow ourselves to have a base of 1. Remember that anything at least exponentially, it's easy to understand why we don't have a base of 1, because it's always 1. But for the same reasons, we don't allow our base to be 1 on a logarithm either. But with b, m, and n being positive real numbers and b not being 1, then we have our three properties are as follows here. The product property states that the log base b of m times n, and that's what I'm going to put in here. I'm going to say that this is our product right here, and just to be clear, let's put parentheses around this. So we're taking the log of a product, m times n. What we get is log base b of m plus log base b of n. And so the very first thing I want to kind of recognize here is this: when you take log base b of m times n, because what you can look at this as doing is multiplying two things with the same base b here, then when you multiply two things with the same base as b, we add the exponents. So in other words, we're going to add these two logarithms together, which is just tantamount to adding the exponents together. So what we see is that we say log base b of a product m times n. We could rewrite this as log with the same base, b, of the first factor in the product, and instead of times, we'll write plus log base b of n, which was the second factor in our product here. Likewise, when we look at the log base b of a quotient, okay, so a quotient m over n, when we divide two things with the same basis, what do we do with the exponents? Well, we subtract them. Well, the same idea is going to happen over here. We say log base b of m, which is the top part of our quotient, minus, instead of divide here, log base b of n. So you'll notice that in either instance of rewriting, all of these bases must stay consistent. It's just that, hey, when we take the log of a product here, we rewrite it as a sum, and when we take the log of a quotient, we rewrite it as a difference. So our last property here is our power property, and this says that if we take log base b of anything to the power of something, then really this n, this exponent here, what we do is we stick it out in front. And we could say that this really the same thing as n times the log base b of m, and this would now be m to the first because we've transported now the n out in front. So what I want to do in this video is essentially use these three properties here in order to evaluate for some logarithmic values for which we couldn't find on a calculator because we lack, say, a base of anything but 10 or e, but also because if we know some given values, we could be able to compose some unknown values using the given values. So looking at this down here, we are given the fact that log base 2 of 3 is equal to 1.585, and also that log base 2 of 7 is equal to approximately 2.807. So when we look at this here, and we look at our very first expression, it says, would you find log base 2 of 3 over 7? Now the thing I want to recognize here is that because we have a quotient, we're taking the log of a quotient, then what we could do is we could rewrite this as log base b, which in this case, okay, our b here is going to be 2 throughout. But we would say that log base 2 of 3 over 7 would be the same thing as log base 2 of our numerator quantity here, so of 3, minus log base 2 of our denominator value here, so 7. So because we are able to rewrite this expression as a difference of two logs here, then we could say that really what this would be approximately equal to is log base 2 of 3, which is given as being about 1.585, minus log base 2 of 7, which is given as about 2.807. So just getting our calculator here, suppose we could just say 1.585. We have 1.585 minus 2.807. We could then say that this gives us about approximately negative 1.222. So I'm going to put a box around this. But the thing we want to do is come up here and say, well, then this is approximately negative 1.222 because we were able to rewrite this as a difference of two logs and we knew their values. So therefore, this one has a value of the difference of those two log values. So looking at this second part here, letter B, it says log base 2 of 21, and what we're seeking to do is use these properties up here, product, quotient, and power, to rewrite this in terms of log base 2 of 3 or log base 2 of 7, for which we know. So what you'll notice is the 3 and the 7. Another way to express this here would be log base 2 of, and we'll just write 3 times 7. So now that we're taking a log of a product, we have a product here, then what we could do is we could rewrite this as the log base 2 of the first factor in our product here, 3, which would be like the m up here, plus, okay, log base 2 of 7, the second factor in our product. So with these, again, we know these values. This is about 1.585, and this is about 2.807, except for this time, what we're doing is we're summing them. So we would say, if I were to pull this back up and instead go back and evaluate this as being a sum, then we get 4.392. So about 4.392, and I'll throw a box around this, but really what we want to do is come back up here and say this is about 4.392. So for this last one here, what we're going to see is this. We have log base 2 of 49. And again, what we want to do is write 49 in terms of, say, 3 or 7. And we could say we could use a product or a quotient, or we could raise to a power. So the interesting thing about this one here is that log base 2 of 49, another way to write this would be 7 times 7. And so that would be in terms of sevens, but what I'm really going to push us to do this time is to recognize that this is really 7 squared. And so because what we have here is the log of something to a power, then we can use our power property. And remember that power property up here says that if you take the log base b of something to a power, then we're going to take that power and put it out in front. So what we could say this is equal to is the same thing as 2 times the log base 2 of 7. And so all we've done is taken that exponent and stationed it out front. The reason why we can evaluate this now is because we certainly have a value for log base 2 of 7. We were given the fact that it's approximately equal to 2.807. So if we were to take that 2.807, and double it, we would get 5.614. So about 5.614. We'll throw a box around this, and then we'll come up here and say that this then must be about 5.614 by the properties that we have listed above. So in the next video, what we'll work on is using these same properties, the product, quotient, and power property, to both expand and condense expressions. Cheers.